The end effector or tool of robotic manipulator is typically mounted on flange or plate secured to the wrist of the robot, or wrist is nothing but hand of robot which is directly connected to last joint. Means the gross work volume or work envelope of robot is defined as the locus of point in three-dimensional space that can be reached by robot arm. Okay, or in another word, work envelope or work volume is defined as locus traced by robot hand in three-dimensional space, or robot end in three-dimensional space. So robots are generally classified according to their number of degrees of freedom or number of axes. The degrees of freedom of robot roughly indicates the capability of a robot. Based on degrees of freedom, 6 degrees of freedom or 6 axis robot used for orienting or positioning of tools. So in that first type of robot, Cartesian coordinate robot, three major axes all are prismatic. The resulting notation for the configuration is triple P. We already discussed in previous video. So these characteristics of Cartesian robot, also called as rectangular coordinate robot, and in that cylindrical, this produce the cylindrical coordinate robot. An example of cylindrical coordinate robot uh, gives a revolute joint, or first revolute joint swing the arm back and forth about vertical base axis, and the prismatic joint means second prismatic joint moves the wrist up and down about vertical axis, and third in and out, or third degrees of freedom in and out along the radial axis, or work envelope of cylindrical coordinate robot is simply cylinder. So in that previous lecture or in that previous slide, we already discussed all work envelope generated by robot arm. So work envelope by Cartesian coordinate robot is a rectangular box. Work envelope generated by cylindrical coordinate robot is simply cylinder. Work envelope generated by spherical configuration robot or polar configuration robot is simply sphere. Work envelope generated by articulated robot is simply sphere. And last one, work envelope generated by SCARA robot, selective compliance and assembly robot, is simply cylinder. So these are the different work envelope generated by robot arm or robot hand, or locus traced by robot hand in three-dimensional space, is known as work volume or work area. So this video shows exactly how you can create work volume or work envelope according to their geometries.
There are four main types of robotic arm geometry: rectangular, cylindrical, spherical, and jointed spherical. Robots with rectangular arm geometry use Cartesian coordinates and move linearly along each of the x, y, and z axes. This type of movement is also called 3P geometry, where the P stands for prismatic or linear motion. This type of geometry is most commonly used with pick and place or large overhead mounted robots. Rectangular arm geometry robots can only move linearly in each direction. An overhead crane robot is a good example of this type of motion. It can move forward and backward, left and right, and up and down. Robotic arms that use Cartesian coordinate geometry generate a rectangular work envelope. Rectangular robotic arms have the simplest geometry and control system and are typically used in material handling operations. Cylindrical arm geometry robots move linearly in two directions and rotate in one other. Since this type of robotic arm moves in two separate prismatic or linear directions and rotates in one direction, it's given the designation of R2P, where the R stands for rotational. This type of robotic arm is most often used in machine tending, assembly, material handling, and palletizing operations. Robotic arms with cylindrical geometry move linearly in two directions. Vertical linear motion is called stroke. Horizontal linear motion is called reach. And rotational motion is called swing. Cylindrical geometry robots have a cylindrical work envelope. The advantages of this type of work envelope is a robotic arm reach that is deep at both the top and bottom of the stroke. Additionally, the robot structure allows for quick movements with high repeatability, a smaller use of floor space, and a larger payload capacity due to structural rigidity. Spherical arm geometry robots can rotate in two directions and move linearly in one, and thus are given the designation of 2RP. The robot has base rotation, shoulder rotation, and prismatic or linear motion at the arm. This type of robotic arm is most often used in machine tending, material handling, welding, painting, coating, and assembly tasks. Robotic arms with spherical geometry have rotational movement in two directions, rotational movement at the base and rotational movement at the shoulder. Spherical arm geometry robots also have linear motion in one direction, typically the reach of the arm. Spherical arm geometry robots have a mostly spherical work envelope at their outer reach, but are limited by the linear reach of the arm and the rotation of the shoulder joint. The shape of the robot's inner work envelope is almost conical and does not become a sphere until the arm extends. Spherical arm geometry robots typically have a very long reach and have proven their performance in industrial applications. However, their high cost, large use of floor space, and lack of flexibility compared to jointed spherical arm robots make it hard to justify in most industrial applications. Jointed spherical arm geometry robots have rotation in three directions, use revolute coordinates, and are given the designation of 3R. They are one of the most popular types of robotic arms and most accurately mimic the movement of the human arm. Robotic arms with jointed spherical or articulated geometry rotate on at least three axes. Left and right movements are provided by rotation at the base. Horizontal movement is provided by rotation at the shoulder. And vertical movement is provided by rotation at the elbow. Except for very close to the body, the work envelope of a jointed spherical robotic arm is almost entirely spherical. The advantages of this type of work envelope is a robotic arm with very deep reach, minimal floor space use, and high positioning mobility of the tool end arm. Due to its mechanical complexity and the complexity of its controller, this robotic arm typically comes with a higher hardware cost and requires skilled technicians.
In that SCARA robot, shoulder joint and elbow rotation axes are vertical. This robot also having two revolute joint and one prismatic joint. That's why the motion configuration of Scala robot is RRP, revolute, revolute and prismatic. The first revolute joint rotates the arm back and forth about the vertical axis. The second revolute joint swings the forearm back and forth about vertical axis, and third joint is prismatic joint with slide wrist up and down. So in that jointed robot or jointed spherical arm geometry, when the last remaining prismatic joint is replaced by revolute joint, so that the configuration is triple R 3R geometry, means figure shows triple R geometry. Or an articulated robot or jointed arm robot is the opposite to Cartesian coordinate robot in the sense that all three of all major axes are the revolute rather than prismatic. Here the first revolute joint swing the robot arm back and forth about the vertical base axis. The second joint, means second joint of jointed robotic arm, pitches arm up and down about the horizontal axis, and third joint, means last wrist joint, pitches again or rotates the robot wrist along horizontal axis up and down. So these are the three rotary motion involved in jointed arm or spherical geometry. So jointed arm robot is exactly opposite to the Cartesian coordinate robot, because all Cartesian coordinate robot having three prismatic joint rather than jointed arm robot having three revolute joint.